Tēnā koutou katoa. Thank you so much for everybody who has come to this, and to my colleagues over the last year or two of discussions as we've pulled this together. So as you've heard already, my own research is in cosmology, which is to say the origin and evolution of the universe. And so many cosmologists might say, by definition, anything we do counts as fundamental or foundational. So anything that I'm doing is necessarily within scope for the centre here. But in fact, at least in my own thinking and my own work, I would make a distinction between the things that I do that are sort of basically bread and butter cosmology. An awful lot of cosmology, in fact, is kind of straight up honest physics. I love it. It taps into everything I know. So physicists, aficionados of physics in the room will recognize these as Landau and Lifshitz, things we use to kind of stress out our graduate students. And most of what you need to know to be a cosmologist lives somewhere in these books. It's a little bit like being a novelist and looking at the dictionary, in the sense that everything that you're going to write is inside of the dictionary, and it's up to you to figure out how to put them together in an order that makes sense. But basically everything you need to know to understand stars, the evolving universe, is probably somewhere inside of these books. The trick as a cosmologist, though, or the things that I would see as being in scope for this Mārama, for the centre that we have here, are really what I think of as taxi driver questions. And so a taxi driver question is this. Imagine for a second you're a cosmologist. For some of those in the room it will be easier than others. But imagine, join me in this, you're all cosmologists and you've just got off the plane in New York and you're going to a cosmology conference. And you pick up a cab from JFK, they're taking you into town, and you get a garrulous cab driver, the one that kind of likes to talk. What are you coming to New York for? New York. And did I do that right? I lived there for a while. I can't do accents. I'm not going to try. And I can't even remember what my own accent is anymore. I went through a long phase of being asked, where are you from, when I came back to New Zealand, and I realised I'd been away at that point for quite some time. But if you say, so the cabbie picks you up and you say, why? They say, why are you in New York? And you say, well, I'm going to a conference. And then they say, what kind of conference? You say, a physics conference. And then they say, what kind of physics? You say, well, I work on the Big Bang. And then they say, wow, that's really cool. Well, sometimes they don't, but let's pretend for a second that we've got the kind of cabbie that does. And you'll get three questions. And the first question is, will the universe expand forever? And we've answered that question. The cosmologists in the last 20 years have answered that question as best as we know. The answer to that question is yes. The universe not only will expand forever, but when we look at a distant galaxy, its expansion rate, its movement away from us appears to be picking up speed. A discovery that won the people responsible for that the Nobel Prize in 2011. And so as much as that sounds like a deep question, that's a question that was answered by people doing business as usual cosmology, not necessarily something that fits into the scope of what we're doing here. But there are two more questions that you get from the taxi driver. So this is, in fact, here's a picture of the way that we answered the question about whether the universe will expand forever. We looked, when I say we, I mean other people, not myself, looked at exploding stars halfway across the universe. They're standard exploding stars. When they pop off, you can tell how bright they are. You can measure how bright they are. You know how bright they would have been. You can then guess or estimate how far away they are. And from that, you can build the expansion history of the universe. And once, with a little bit of extra effort, you can answer that question. So we've had strong suggestions that this was the case since the 1990s. It was a deep question, but it's one we answered from inside of astrophysics, essentially. But the other two questions are, what was there before the Big Bang? And were there Big Bangs other than our own? And those are much, much tougher questions to ask. And I look at this, and there's something, I had a beautiful picture of my parents' wedding photo here. I'll see where it's gone. Oh no, here it is, brilliant. And so it's coming. No, my parents are coming next. That's not my parents. This does not look a bit like my parents. So let me do it this way. Here's my parents. So the question, are there Big Bangs other than our own? Are there other universes apart from our own? Those are things that by definition we are unable to sense or detect. Everything that we are physically able to observe and see lives inside of our own universe. But if the Big Bang is an event, and we don't know what the Big Bang is, if the Big Bang is something that can happen multiple times, then it's very easy for both the taxi driver and for a professional cosmologist to ask, did the Big Bang happen more than one time? Has it happened many times? Do we live in what is colloquially known inside of the field as the multiverse? Is there more than one universe? Likewise, did our universe genuinely come from nothing? Or was there some previous universe that preceded it again? There's not necessarily any remnant of that would be left over in our universe for us to find and observe. So these are questions that we can ask as physicists, but it's very, very hard for us to know how to answer them. Because in many cases, the physical suggestions that this is true are also telling us that the laws of physics in each of these universes can be different from each other. So if you were to imagine building an LHC, a Large Hadron Collider, in each of these possible universes, the Large Hadron Collider would discover a different particle physics in each case. Not all of those versions of particle physics, maybe even most of them, would be compatible with the existence of atoms, would be compatible with the existence of chemistry, and therefore would be compatible with the existence of beings as we know and understand them. In other words, there would be no life in those universes. The question of what do we mean by life is something that I can throw to my colleague Emily. How would we define that well enough as a physicist to be able to answer that question? And secondly, if it turns out that our universe is in some ways weird and unique in ways that allow us to exist, the question we are asking then is, how would you feel if your parents had never met? Because we can only ask questions about our existence if the universe is such that we are able to exist inside of it. And so as a physicist, I don't necessarily know how to tackle the probabilistic versions of those questions, but I'm willing to have a go at them. And in fact, with some of my colleagues, my student Nathan and my colleague Ben Schleer, we have the opportunity to ask some of these questions around the way that the Big Bang might have worked, the way that the Big Bang might have happened, and how that would play out. And so those are the things, the sort of subset of things that I do as an astrophysicist and a cosmologist that I feel are in play in the context of Te Ara Mārama and the Centre for Fundamental Inquiry. It raises questions about how we do fundamental statistics. It also raises questions about how, sort of fundamental questions inside of philosophy, how we think about our existence if we're not able to, in a world in which our existence itself is contingent. So my mother and father, if those people hadn't met, I wouldn't exist, but also I wouldn't be able to theorize about the odds or probability of my existence. So how do I make sense of that as a cosmologist? And so one of the ways, just to provide one example of something that has a little bit of teeth, a little bit of meat, one of the ways that we make sense of this in cosmology is what we call the landscape. And so the landscape is an idea that pops up in the context of string theory. And string theory is supposedly a theory of everything. It's a theory that explains all of particle physics and all of the interactions between those particles. So if it explains everything that exists in the material universe, one of the things it has to be able to do is to explain questions about where did the universe come from, how did the Big Bang work, what was the universe like right after the Big Bang, were there other Big Bangs? All of those questions, some answers to those questions in some sense should live inside of string theory. Going through the 1990s, there was a lot of hope that string theory predicted a unique formulation for the way that particle physics was supposed to work. And so things that are mysterious, why is the electron mass this? Why is the proton mass this? We thought might be in some sense, string theory was telling us that it would be those ways because it couldn't be anything else. The problem is as we studied string theory in more detail, we realized that string theory potentially allowed the existence of not only hundreds of thousands of millions of universes, but potentially 10 to the 500 different possible configurations of the universe. So 1 followed by 500 zeros, a large number. And we can model this as by saying that the string theory landscape is something that looks like this, except not a two-dimensional object, but potentially a 300 or 400 dimensional object. And each point where there's a minimum, where you can't walk further downhill, corresponds to a particular configuration of our universe. And our whole universe lives at one of these points. And so the probabilistic question here is that it turns out that there's a waterline in this landscape. And our universe can't exist below the waterline, because if it did, it would recollapse. And it can't exist a long way above that waterline, because if it did, the universe would expand so quickly that anything inside of it would be quickly blown apart. There would be no stars, there would be no galaxies. There might be atoms if we were lucky, but there would be nothing else. And so the way that we're trying to ask this question probabilistically is how many of these 10 to the 500 universes would exist just far enough above the waterline for them to correspond to something like the universe that we see today. And we can't write down a formula for the landscape, it's very complicated. But then people say it's so complicated that it is almost random. It's random in the same way that the exact shape of the surface of a wind-blown lake is random. It's got many ripples on it, and we can treat that using the mathematical theory of random functions. And so what we wind up with is something that looks like this. And so if I just click this here, hopefully the seawater will rise, and we're going to ask for different configurations of the landscape. What fraction of those configurations would be just above the waterline? Would that fraction be exactly 0, in which case our universe and string theory are not compatible with each other? Would it be such that not only that fraction was not exactly 0, but the height of the minimum relative to the waterline would be very different from the ratio that we see in our own universe? Can we get any leverage on this problem by developing this theory of this mathematical theory of random functions in combination with our understanding of the shape of the landscape that's suggested to us from string theory? So this is where we're working. This is the particular problem that I'm working on. People who in the room who are interested in the theory of random functions. It turns out we've actually, in the process of doing this, we've previously discovered new relationships in random function theory and random matrix theory that I think gets me invited to random function and random matrix conferences. Who knew that that was a thing? But they're in Italy, and they're fun. So we're still working on this. It's in some sense a very qualitative approach to a very hard problem, but it's also, when we're actually doing it, it's an extremely quantitative calculation. And so we understand, we're understanding that our results here may impinge on philosophy as much as they do on physics. But that would be an example, to give an example of something that we're bringing, or that I feel that I'm bringing outside my own work in the context of the Centre for Foundational Inquiry to Mārama. That would be the piece of my job that I feel like I'm doing. So, throwing to my next colleague.